Hello, my name is Andre Eberspacher. I am currently in my second year of research with the Kranz Group as an undergraduate. I major in both chemistry and philosophy, and I have a specific interest in the philosophy of science within the realm of science communication. The video presentation of this poster will begin with the leftmost column and work down each column from left to right. Due to the limitations of this video submission, many more detailed explanations have been cut for time, and I hope you are able to see me on the presentation floor so that I can clarify some of the concepts I am about to refer to. The group I work in published evidence in 2020 that the sterically hindered octahedral vanadium 5 Schiff base catecholate complex depicted here was 12 times more cytotoxic to glioblastoma cells than the conventional chemotherapy drug, cisplatin. The graph depicted here shows the viability of glioblastoma cells compared to the concentrations of both cisplatin and the vanadium catecholate complex. We refer to this compound as vanadium oxide HSHED diterbutylcatechol, catechol, and it is currently our leading compound. In the past year of my research, I have attempted to characterize the structures of a selection of the Kranz Group's most promising vanadium compounds for intratumoral injections. Initial attempts involved two methods of growing crystals of these compounds. In these attempts, I was unable to produce a viable sample for single crystal X-ray diffraction to determine their structures. The research I am presenting here shows how using multiple kinds of nuclear magnetic resonance spectroscopy, or NMR spectroscopy, gathered the data we needed to identify the major isomer of the leading compound in organic solutions. We collected this data in organic solvents because we believe the major isomer of this compound is unlikely to change in solutions that mimic conditions of the human body. Depicted here are the four possible isomers of vanadium oxide HSHED diterbutylcatechol. Catechol. The difference between these isomers are shown in red circles for easy identification. The asymmetric catechol ligand has two possible coordination modes, and the ethanol arm above it is a stereocenter with multiple possible conformations. It was my goal to identify which isomer is most abundant in organic solutions using NMR spectroscopy to inform further research to understand its bioactivity while developing my own familiarity with NMR spectroscopy. Included here is the synthetic scheme that we follow to create this compound. Depicted as a reagent is the aforementioned catechol. If you imagine it as a piece of paper and can flip it over in your mind, these transitions through 3D space are what make the multiple coordination modes of this complex possible. At the top of the second column are my methods. Included here are the instruments used to gather NMR spectra and some of the parameters they were set to in order to achieve this task. Making sense of NMR spectra is far from simple. This form of spectroscopy relies on the results of quantum phenomena, which are difficult for our minds to grasp. I hope the following synopsis of nuclear magnetic resonance serves you well, and a link to a more detailed description can be found in the video description below. Included on the poster in this section are an image and description to aid in understanding what a Fourier transform does, and a visual aid to understand what is happening inside a sample inside an NMR spectrometer. NMR spectrometers output a spectrum that is the result of a Fourier transform run on a sine wave, derived from a radio frequency signal caused by atomic nuclei, in this case hydrogen nuclei, realigning their spin orientation within a magnetic field. The Fourier transform takes the multiple frequencies within the radio signal and separates them into peaks that you see in NMR spectrums. These peaks correlate to the frequency at which the spin orientations of atomic nuclei relax into the magnetic field generated by the NMR spectrometer. There are multiple types of NMR, and the one most useful in our attempts to characterize this compound was nuclear Overhauser effect spectroscopy, or NOESY. Both of the axes in a two-dimensional spectra, such as that in NOESY, are formed from the one-dimensional NMR spectroscopy seen above it, and the center of the graph in 2D NMR shows the interactions between atomic nuclei. A diagonal line from the bottom left to the top right shows where nuclei are interacting with themselves. However, We are only interested in the off-diagonal signals we see on this graph. The nuclear Overhauser effect results from interactions between atomic nuclei through space less than 5 angstroms across by measuring the transfer of nuclear spin polarization from one nuclei to another via cross-relaxation. Further down in this column, we see a vanadium NMR spectra. Vanadium NMR focuses on vanadium-51 nuclei instead of hydrogen. Because there is only one vanadium atom in each of these complexes, but we see peaks at multiple points in the vanadium NMR spectra for the various solvents listed, we know that these vanadium nuclei are existing in slightly different chemical environments, causing them to relax back in line with the magnetic field differently. The existence of different chemical environments in this case is how we know there are multiple isomers of this compound in solution. Now, at the top of the third column, we see the NOESY NMR spectra from before, zoomed in to show the off-diagonal interactions crucial to identifying one part of our major isomer, the coordination of its catechol. At the peaks we labeled HY and HE, we see an interaction. I have drawn lines on the graph to make this easier to see. We know that this is between the terbutyl group of the catechol and the nearest hydrogen on the aromatic ring of the HSHED backbone. Depicted below the graph is a structural representation of the complex with the labels of each of the peaks on the NMR spectrum, with a red arrow showing the interactions between the hydrogen nuclei I am speaking of. To the right of this image is a model generated using computational chemistry. It shows how a relatively large distance between one of the bonds between the vanadium center and an oxygen on the catechol ligand allows for oscillation between coordination modes of this ligand. In conclusion, using 2D NMR techniques, this study helped elucidate the solution of the structural isomer of an important vanadium-5 complex currently being tested for its anti-cancer properties. Thank you.